Hello, it's Keith here, and this is lesson 6 of the platform-specific series of my Z80 assembly programming tutorials. Now, we've been looking at the last few weeks at how to get bitmap graphics onto the screen without using the firmware. We're now going to take this further, and we're going to start learning how to read the keyboard and the joysticks of the systems, again, without reading the firmware. And the benefit of this is, if we don't use the firmware and we write our own functions, and we write functions that work in a common way across all the systems, we can write multi-platform software very easily. And I'm actually going to sort of start proving this over the next week, and I'll be putting it onto YouTube over the coming months. I'm doing a 7-day programming project where I'm going to try and write an old a conversion of an old DOS game called Grime, and I'm going to try and write it in a way that compiles onto 11 different systems. That's including the MSX1 and 2, the Spectrum, the Amstrad CPC, the Enterprise, the Sam Coupe, the Sega Master System, the Sega Game Gear, and the Game Boy and the Game Boy Color. And bearing in mind the Game Boy and the Game Boy Color aren't a true Z80, but if we are careful and if we write our own common modules that can work on all the systems in the same way, we can write logic code, one piece of logic code that will work with the with our own hardware code that talks to the graphics and the sound systems, and that makes our game programming quick and easy. And I'm going to prove this, hopefully, by making one game in 7 days. So if you want to see that, please follow my channel, and you'll see how that goes. I'm hoping it's going to go pretty well. But anyway, today we're going to be looking at the start of how to read from the keyboard and the joystick. Again, these are platform specific, so we're going to look at the hardware and we're going to split it up again. Today we're going to look at the Sam Coupe, the ZX Spectrum, both those systems are very, very similar, and the Amstrad CPC, because the Amstrad CPC is always our sort of main system in these tutorials. Now, to be able to do this, we do need to understand a bit about how the hardware of a keyboard works, and for that we're going to have a look at the website. There's always a website that matches these video tutorials, but we're going to have a look at these graphics here because I've collected and drawn some pictures that will hopefully explain things. So, well, how does a keyboard work on an 8-bit system? Well, keyboards in general, and this is true for modern keyboards as well, the way they work is you have a plastic membrane, and this membrane has electrical wires printed onto it, and there's 2 layers. Now, each layer has a set of wires, and it will be around 8 or 10, and those wires will pass through multiple keys. So the top membrane will have about 8 or 10 wires, and each wire will pass through half a dozen keys or so, and the bottom membrane will also pass through half a dozen keys. But there will only be one key where the membrane, the top and bottom membrane, join together for each unique key. And so if you imagine we had a super simple membrane where the keys were literally in a grid, it would look like this. So if you imagine the blue is the bottom membrane and the red is the top membrane, you'll see that there's no, and if you imagine the crossing point in magenta here is the keys, there's no 2 keys that have the same membrane, blue and red membrane combination, because if there was, it wouldn't work, because the system wouldn't be able to tell which key was pressing. So when a key is pressed down, the 2 membranes connect together, and this creates an electrical short circuit, and this means that the hardware can see that those 2 keys have connected together. And because the keys are all unique, this key being down, when this key is down, these 2 lines will short. It can tell from the top and bottom membrane combination which key was pressed down. So in this case it was this one, but if it was this one, then this line would have been shorted with this line. So it can always tell which one of the keys is pressed. Now this works fine, but there is a problem with it. This is something we do have to be aware of in computer gaming. It was especially a problem with Chibi Akumas because of the amount of keys I used. Now, because there is sharing between the keys, if the wrong combinations of keys are pressed, it becomes impossible for the computer to tell which keys are actually down. Now let's imagine that these 3 green keys are pressed here. Now this will light up this wire, this wire, this wire, and this wire. But you'll notice these actually join at a 4th point, which I've marked in yellow here. Now the system can't tell which 3 of these 4 keys are held down. It can't even tell if actually all 4 are being held down. And because of that, when these 3 keys are pressed down, you get a shadow key pressed down here, and this is called key clash. And depending on the layout of the keyboard membranes, the key clash will occur in certain places. Are different on different systems, so it's very unlikely that the same keys will cause clash on different machines because the membranes are physically wired up differently. But it is something you have to deal with. All you can do is select the keys that are least likely to clash. It would be very stupid, for example, to select this key for up, this key for down, this key for left, and this key for fire, because you would not be able to you'll be firing erratically when you are pressing your control keys. But as I say, it's an unavoidable fact of these keyboards. You won't need to know it in the early days, but if you're creating games, you will find it can happen to you, and you just have to deal with it. So I just wanted to explain what a membrane was. You can see one here, two membranes. You've got the grid, which is my imaginary layout, and the key clash. Now, we don't need to worry too much about it when we come to actually programming our computer, but you will, if you understand this, you will be able to more clearly understand why the code is doing what it's doing. And the procedure for reading in a keyboard is quite simple, typically speaking. So if you imagine that these are different ports on the system, all we do is we probe each port, we read in a byte, and the lines that are not pressed are 1, and the lines that are pressed are 0. So if we read in this line, for example, here, then we would find this bit would be 0. Why 0? Well, I said earlier it shorts the line that's been pressed. So if the 1 is sort of high and the 0 is shorted to low, so that's why you get that inversion of the bits. But it doesn't matter; our code will deal with that. So that's kind of the introduction to the hardware of the keyboard. If you don't understand that, don't worry about it. You don't need it to do this, and really the stuff we're going to be going over today, you don't really need to know too much about at all. Really, you can use my code, you can base your work on my code, and my code is actually based on other examples I've seen online. So if you don't understand any of this, then you can just skip over this, but I think it's worth you having a look at the code because it's quite complicated, and it's worth understanding to some extent how the hardware works, because that gives you the strength of when the limitations like key clash come across, you'll be able to understand why they're happening. And if you need to change the code and optimize it, you won't be accidentally deleting bits that you think aren't needed when actually they are. So the example today, this is the example code we're running. It's very, very simple. All it does is it uses this scan keys function to read in a character. This is a direct hardware character, and then we print it to screen. Now, we're not actually going to look at this scan keys function today. The reason for that is we're going to look at it after we've looked at all the hardware systems in a few weeks' time. But all it's doing is it's converting the key press inputs from the lines that I mentioned here, the bits that are being pressed down, and then it's working out what the key that actually represents. And if you're pretty sharp, you should be able to work out how that works from what you see today. But if you don't care or don't understand it, don't worry, because all you need to do is download these examples, and the function that does this scan keys wait char function, keyboard driver and scan keys, these are the functions you need. And the scan keys is the multi-platform code, and this one is the platform specific code that branches out to all the different systems. And as I said, we're going to look at 3 systems today. So here's some examples of the code being used. So here's the Amstrad CPC, here's the ZX Spectrum, and here's the SAM Coupe. And you can see if I press the letter H, you'll see a H key appear. A letter H appears. A key. Press the 0, and a 0 key appears. Now the same is true on here. If I just press the 0 key again, and the same is true on here. But one thing I can't do, if I press the backspace key, you'll see it prints a weird symbol. If I press the escape key, we're actually getting an E, and that's something slightly odd, but you'll see why it's printing an E later. It's because I've actually told it to. So you can see that while we're reading in the keyboard correctly, we're getting some odd artifacts because we've not got any functionality behind that. We're not processing escapes or backspaces, and the code here would actually have to do that, but I simply haven't programmed it to do that. So what are we going to look at today? Well, let's take a start by taking a look at the ZX Spectrum. So how do we read in keys on the ZX Spectrum? Well, let's take a look. So here's my website again, and the way we do it is we set C to port FE. Now FE is always used for the keyboard, and then we set B to all be 1s with the exception of one bit, which is a 0. And the position of the 0 defines the line of the keyboard that we're reading in. So if bit 0 is 0, then we're reading in the line that has shift Z, X, C and V. And you'll notice there's actually only 5 bits in use, which is rather unusual on the Spectrum. All the others actually use all of the bits. But anyway, and then if we shift the 0 along, 1 to the left, so it's in position 1, we read in A, S, D, F and G. And then we shift it along again and we get Q, W, E, R, T, and so on and so forth. Now, the ZX Spectrum does have a special joystick port called the Kempson joystick port, and if that's present, we can read that in from address 1F, which is actually 31, very low. but and then we can read in 5 bits, which represent the up, down, left, right and fire of the joystick. So there we go. Now one thing to note is on the ZX Spectrum, if we try and read the Kempson joystick without one installed, it will malfunction, and because of that I've got a function called allow joysticks, which uses self-modifying code to enable joystick reading. It's disabled by default to avoid that, and we're not going to use the joysticks today, we're just going to read the keyboard, but the procedure is basically the same. So as I've said in the past, the ZX Spectrum uses a 16-bit address bus, so we're using B and C, and we set C to FE, as you can see here, and then we set B to the definition of the first line with that 0 at the far right. So now what we do is we read in the byte into 8. Now, as I've said, it only uses 5 characters per line, so we've got 3 bits that we don't want. And the way that this code I've written works is, as I've said before, 0 is low, that's a key that's down, and 1 is a key that's up. So we need to default the keys that are up to 1, so that the keys that don't exist, sorry, to 1, so that the generic code will work with the keys in the same way and not malfunction thinking that they've actually pressed down. So that's why we're doing this OR here, just to reset those non-existing keys. We then store it into this buffer HL, which is this keyboard scan or key presses buffer that is used on all of the systems in this tutorial, and that saves the hardware key presses that can then be converted into joystick presses or keyboard presses, and we'll see how we do that in a moment. So once we've saved this keyboard press, we then move HL to the next memory address. We then set the carry flag so that the carry is 1, because we're then going to rotate everything to the left, and that will shift this 0 bit along to bit position 1, and it will put that carry bit on the far right here, and that will give us this value here. And so that's how we move along to the next line. We then repeat until we get the 0 out of this rotation command, and that means we've reached the end of the Spectrum's keyboard matrix, because as soon as this 0 gets popped off, there's no more lines to read. Now you'll see there's the return command here, but I've put my marker for self-modifying code here, because if we've turned the joysticks on, we will then do another read, and we read in the line from the joystick port, and then we again we set the 3 bits that aren't used to 1, and then we save that in the hardware keyboard memory presses address. Now when it comes to actually converting them, as I say, I do have some code we're going to look at a later date, but basically it's very simple. All we do is we go through the bytes we read in, and we check which bits are 0, and when we find the bit that's 0, we look it up in this table here. And this table is in the same format as we read in, and each key press is converted here. So you can see you've got this hash symbol here, and I've used that actually for the shift key, because I had to convert it to some kind of alphanumeric, some kind of ASCII character. I thought, well, hash will do for now. We can always convert it later, and we can define our own, like this is 13, and I think this is 9 or something, but we can set these to anything we want. They don't have to be the actual key presses the keys really represent. It's just handy for basic data entry to do so. So as you can see, each key here is represented. They're just in the opposite order, because that's the order I process them when it comes to reading the keys in. So there we go, and there's just a little bit more information here which I copied out of some tutorial, I think, and this is the numeric, this is the decimal numeric value of the ports and the key presses on that line, and that's the ZX Spectrum covered. Now the SAM Coupe will look very familiar, because we've covered half of it actually. The SAM Coupe's keyboard is based on the ZX Spectrum's. If you look at the ZX Spectrum's keys here, you will see that they're exactly mimicked in these red keys here. The way the SAM Coupe has a better keyboard, because to be honest the Spectrum keyboard's rather lacking, and what they've done is they've added an extra port which fills in those 3 bits that the ZX Spectrum didn't use. So we have to read in from a second port for the extra 3 bits, and then we have to read in an extra line here as well for the cursor keys. So we've augmented the Spectrum's keyboards with these magenta keys here, but basically the procedure is almost the same. So let's have a look. So again, we load B with the value here, with the bit 0 at the far right, which is the first line. We load C with F9, which means we're loading in the extra SAM Coupe bits first, these these ones here. So we read in the byte. We then keep only these far right 3 bits here. We store it in HL. We then load in the ZX, the one that's the same as the ZX spectrum, FE here. We read in a byte from there. Keep only the right 5 bits here. We then OR in the 3 bits we read in before here, and that gives us the combination for the entire line. So we then just save it back to HL and move HL along. Again, we're using the same key press array here. Once again, we set the carry flag, shift all the bits across to the left, check if we've popped off the 0, and if we haven't, we repeat again. And then finally, all we need to do is we need to read in this line here. Now, to do that, we just load B with 255. We read in the bit here, we read in the byte here. We wipe out the top 3 bits, and we have nowhere to read them from this time. And then we store that as well, and we're done. Now, there's no Kempson joysticks on the Sam Coupe, and I should have said earlier, on the ZX Spectrum, the non-Kempson joysticks, they all map to the letter keys anyway, and that's true of the Sam Coupe. Its joysticks map to letter keys, so by reading the keyboard we can handle joysticks. And if you're wondering about, well, what keys do they map to, well, you don't need to worry too much, because when we cover the how to use the joystick, I've actually got a redefine keys function. So rather than prescribing forced keys that the user has to use, we can let them select their own keys, and that way they can use whatever they like. And that also allows us to not worry too much about key clash if we're supporting lots of systems, because the user can decide what keys they want for themselves. So very simple there for the Sam Coupe, because it's virtually identical to the Spectrum. And again, we've got the key map here. You'll just notice you've got the extra keys here, and the cursor keys I've just mapped to the C for control, up, down, left and right. So it would actually print these letters to the screen if I press them. We would probably want to put those to a special character code or something that we could more easily process, but this is just test code, so it doesn't matter too much. So that's the Spectrum and the Sam Coupe covered. Now on to the Amstrad CPC. Now the Amstrad CPC is actually a little bit more tricky. Why is that? Well, it's the way that the Amstrad CPC's keyboard is connected to the system. The keyboard is actually connected to the AY sound chip, because the AY sound chip, as an extra bonus, can read data in from devices. And to make it a little bit tricky, because that was already not confusing enough, it's actually connected to another device called the 8255 PPI, which is a sort of bridging chip that we have to use to configure input and output. So we have to talk to the PPI, we have to talk to the AY sound chip, and between the two we can actually get the key presses that we want. But honestly, once we've done all of that faffing around, getting the data in from the keyboard is not too much different from on the ZX Spectrum, really. The ports are numbered differently. This time we're going from 40 to 49, and we are using all of the bits again, but apart from that, it's very similar. We do have a dedicated joystick line here for joystick 1. Joystick 2 shares some of the key presses, but apart from that, it's all very simple. Now, let's have a look at the Amstrad CPC code then. So, we have to talk to this PI device to get it to do what we want. The first thing we have to understand about it is the PPI itself uses 4 ports here. So for F4, anything starting F4, remember it's a 16-bit address, but anything starting F4 is a command to port A. Anything starting F5 is a command to port B. Anything starting F6 is a command to port C. And anything starting F7 is a command to the control port. So what do? Well, first we have to tell the ports whether they're to be set to read or write. So first we send this command here, which will tell the PPI that both ports are going to be writing. And then we load HL to store our data, our return data, exactly the same as every other time we have. We then send the data to the port here, and that will say that we're writing to these ports. Next, we want to set the AY register 14 on PPI port A. Well, why do we do that? Well, register 14 is the register that will read in the keyboard. As I say, we need to tell the AY sound chip that we want its keyboard. So once we've set the 14 to the sound chip, we then need to tell it what that 14 meant, and we do that by sending this command here. F6C0 will tell the system that we want to select that as a register, because F4OE says here's some data. The data is the number 14, OE, but then we need to tell it, well, actually that was the register number we want to select, please, and that will do that. Next we need to send an inactive command, which is just to sort of let things clear down. You have to do these, otherwise you're going to get malfunctioning, so you do need to do that. And next we want to tell port A that we want to read and port C that we want to write, so we send this command here. These are kind of stock commands, you don't need to worry about these and you shouldn't need to change them. As I say, it is quite complex, but you'll see other tutorials like this that use a similar code, so just find one that works for you and just keep it as it is. I did a lot of optimization on this when I was doing the Chibi Akuma's code, but it was originally based on someone else's example. I just swapped some of the registers around to try and reduce the amount of resetting registers. So now we want to select a line, so we need to send the command F640 to start, and so we send that out here, and then we need to read in from port F4 to get the results of the key map. So we load in, we use E here, which is set to F4, we load that into B, and we do an in command here. Now we're using INI, which reads in and saves straight to HL. Now this is a tricky command because, as I've said before, on the machines with 16-bit ports like the Spectrum, Coupe, Amstrad CPC, it alters the B variable, the B register, because it assumes the B register is going to be a counter, and usually that would break the command, but we are resetting B repeatedly here from these other registers, so it won't actually cause us a problem in this case. We then increment A to move to the next port, because we're sending it here to select the port. We then compare to C, which stores our end counter, and if we're not done, we just repeat again. So all of this, it's a pain, but all of this is really just repeatedly saying, this is saying select this line, this is saying read this line, and this is setting B to be correct for the memory address of the port that we need to read from here. So we're repeatedly hopping between F4 and F6 to do our reading in. Now, as I said before, there's nothing special we have to do on our joysticks, so we don't need to worry about that. But the last thing we do have to do is we have to reset the PPI ports so that both ports will write again, because if we don't, we'll probably cause problems for the firmware or our sound effect routines or something like that. So we have to reset everything to out here. And we do that with this sort of stock command F782 here. And, you know, as I said, it's confusing, it's odd, but that's how it works, and you can use it just as is here if you're confused by it. And then once again, we've got our key map here, which is the equivalent key presses of the bits in the resulting array of data. So there we go. Now, that's the end of today's lesson. We're going to cover the other systems hopefully all next week, and then later on we are going to go on to, as I've said before, the Game Boy and the Sega Master System. They're actually easier systems. They have no keyboard, so we don't have to read the key presses, but we will read equivalent joystick presses. As I've said, we are going to have joystick code, and we will have compatible joystick code for those systems as well. Once again, I'm going to be using all of my tutorial code in my so-called Grime Z80 project, where I try and recreate the old DOS game onto many systems. We'll be sort of using it as a sort of proving ground for the code I've been using in the tutorials. I'll be heavily basing it wherever I can on the tutorial code, and anything I find that's inadequate or I have to add, we'll be looking at again later. Once we've moved on from the keyboard and the joystick, we'll then start looking at sound, some more advanced graphics maybe, all kinds of extra things. So please follow my channel if you want to see some more. Hope you've enjoyed today's lesson. Thanks for watching, and goodbye.